next speaker is Bumsig Kim, who got his PhD in mathematics in 1996 under Aug14Thu at Berkeley. It seems that each lecture today has a Berkeley contributor to it. An interesting fact. And he's going to talk about, where's the title? Tell us what you're going to, there it is.
And also, it's a great honor to be here, especially this ICM in Seoul, Gangnam area. So actually I'm from Kango, so this is my style. Okay, I'm going to give you just a rough plan of my talk. So expect to be non-singular projective variety.
Maybe it's better if you use the microphone.
Combined variety, and L is a line bundle, M-line bundle. And mainly we are interested in compactification of the mapping space NGK, XD, which are collection of the pair of pointed smooth projective curve and mapping F from C to X with that degree. We know that there is a well-known compactification using the notion of a stable maps. And in this talk, for a certain GIT quotient target X, so when X can be written as a certain GIT quotient way, we show other way to compactify it depending on the parameter epsilon. Particular case when epsilon is larger than 1, that space compactification which actually coincides with conjecture stable map compactification. And in the extremely other case, when epsilon is smaller enough, this compactification is closely related to mirror symmetry, which I'm going to explain a little bit. Here are some references for my talk. So for epsilon, we're going to have that compactification will be denoted by Q. Q means Quasimap, based on these two papers, Aug14Thu and Seoul. And also we have a purpose formula comparison for the varying epsilon. So we have lots of complication, and we want to compare the virtual quantum class with the modular spaces. And next one is you can further generalize this kind of construction, keeping weighted marking, just like the Hesse did for modular space of stable curves. Because it has some applications in the mirror symmetries. That's the reason we consider such kind of weighted marking tool. This also appears in my talk. And when the target W mod G becomes orbifold, also that this kind of complication could be done in this paper with the Aug14Thu and Theorem has application to mirror theorem for toric dilemma for the stacks. Okay. And also we can slightly twist the mapping data by omega c, so that it's not going to really map, but some kind of sections to get the some examples of modular examples with symmetric obstacle theory, which this notion was introduced by previous talk of Kai. Okay, so here's a setup of target, GIT target. Let W is a affine variety acted by algebraic reductive Lie group. G and fix a one-dimensional representations, some linear action here using character. Of course, then in this product space, we're going to have a G action, right? G act on W and also linearly on the C side, which could be considered as a G equivalent line bundles. Now, we're going to have in the setup, we're going to have four quotients. First one is affine quotients, just taking the stack of the G invariant ring, stack quotients. So that's some some space, kind of orbit space, and but geometry obtained by pretending G act on W freely, so that the, for example, line bundle on this space stack quotients, nothing but G equivalent line bundles on W. Also, the meaning of when we have a map from A for I to Y to stack quotients, this bracket U means that we have this triple Y, P, U, where P is principal G bundle on Y, and the U is equivalent G equivalent map from P to W. So P is principal G bundle, so we have action, right action. And this U could be also considered as a section of fiber bundle. Next, this is a usual GIT quotients, defined by taking truth. And the stack quotients, just taking the only semi-stable locus with respect to theta. This WSS is going to be just certain open subset inside of W, and just take a quotient of that to get a GIT stack quotient inside of this bigger one. In fact, in my talk, these two red ones will be a main object, main target, and this will be geometric target, and this is some horrible target, but going to be used to compactify the modularized space of mapping from curve to here, allow that the map sometimes goes to also outside of semi-stable locus. This line bundle, the G equivalent line bundle, as I said before, also considered as a line bundle on stack quotients. So that by restriction, that's also line bundle here, and we will think this theta as a certain kind of ample line bundle on here or here or here on the stack quotients to measure the degree of the mapping. So that I explained in the previous slide. So in my talk, I'm going to assume that the action on the semi-stable locus, defined this way, has only finite stabilizers. That's important assumption. So that we're going to obtain this commuting diagram, not square diagram, just commuting diagram. So this is stack quotients. So W much G, so whole ambient space, and inside of it we have open subspace, open substack. Using linearization theta, we define the WSS here, and we have a proper map and a projective map as usually. So here are examples of those target quotients, weighted projective spaces. So given integers AI, we can have an action of C star on the Cn plus 1, and with that theta, this part will be just weighted project space as an obifold. So it has some obifold structures. but the full ambient space one has one more some kind of stacking point, the origin. So the origin, so that origin has the continuous isotropy subgroups, so that this point is not an obifold point. In that sense, this W-G not obifold, but it's called Artin step. This one is in the algebraic geometry is called the Dillon-Mumford step. It's nothing but kind of obifold space. So we have also the Grassmannian example, and next toric Dillon-Mumford stack. But in this case, we have many various choices of the theta to get a different Dillon-Mumford stack, even given W and G action Z. There are many choices of theta to get different GRT quotients. The last example will be any projective variety, but later on, to get a nice theory, we're going to assume that it's going to be complete intersections, so like a hypersurface and intersection of the two transport intersection to hypersurface, something like that. And in that case, that X can be also described as a GRT quotient by taking the affine core. But this ambient space, of course, contains the origin, this zero. That's the stacking point. So, but in my presentation, then I'm going to assume that the all G action semi-stable locus is 3 for simplicity. Now, using the target, on the target we have the line boundary and theta, so that you can talk about degree of a map like this way. So given map, the degree is defined as this degree of a pullback of line boundary. Now we were interested in this mapping spaces, so collection of all this pair of the pointed curve C and mapping U. Now you're going to allow that this pointed curve C has also obifold, the nodal singularities, so that this C X I together will be pre-stable curve. So C might have some nodal singularities. So this is a very large spaces. Now we're going to have a very natural commuting diagram of morphisms. So here there's a collection of this pair, but the U, as I said, is a pair of a principal bundle at the section U, so that for getting section data U, we can have this morphism view. So from N to Bumsig, because Bumsig is defined to be just collection of a curve and principal bundle. Also the U and phi is defined a similar way, because M is going to be just collection of domain curve with markings. And it's very easy to see that this modularized stack MGK, just collection of pre-stable curve, is a smooth Artin stack, it's a smooth. And also this phi morphism. So in the phi, just forgetting principal bundle, also deformation of P will also has no obstruction, so the phi is a smooth morphism. Hence that the natural obstacle theory to consider for M GK WMGD is relative view, and for for this relative option theory, the deformation space going to be just deforming U, so the section space will be deformation space, and the first higher cohomology will be the obstruction space when W is a vector space. Now, so in my talk, questions to address the following. So we had linearization theta, and using theta, can we impose stability conditions to single out the Mumford open source stack inside of this very large some Artin stack, which is not much geometry. So, but containing the original space we like to compactify. And in addition, observed theory is perfect. They will have a virtual fundamental classes. Hence, we get an invariance of the quotients. And the question is that when is the observed theory is perfect? And how did the third question is we have gonna have various complication depending on epsilon, so that we'd like to talk about some word processing. So first, for the stability conditions which I'm going to impose, so here's a list of definitions. First, so for any map from curve to the stack quotient, we will call that the pre-image of the unstable locus. This the WS is the complement of semi-stable locus, WSS. So we have the WSS here, but the complement of WSS will be denoted by WUS, and the pre-image of it is called base point. And for such a map, U, we'll call that it's a Quasimap, data Quasimap, when there are only finite many base points. And for such a Quasimap, we'll call that it is pre-stable if the base points are away from the special point, nodes or markings of C. So nodes and markings must be landing on the geometric part, the semi-stable locus, WSS. For such a pre-stable Quasimap, and for any point x in C on the curve, we can define this some kind of a length local by taking the local intersection number of the curve C and this locus. So this is a local intersection number at x, but yet, of course, this general unstable locus going to be generally not a divisor, but you can define that this intersection number using the exceptional divisor on the polynomial. Now lastly, now we come to the notion of a E-stable Quasimap. We will call that in addition, if these two conditions are satisfied, then we'll call that it's an E-stable. So first line, it's about this positivity of the certain Q line bundle on C, and the second one is some inequality control the length Lx. And we're going to call the genus 0 rational component of the curve C a rational tail if it has only one node, some attaching node, and no markings. So rational, when I say that rational tail, it means that some attachment of rational one of the some major part of curve C, but with low markings on that rational tail. So on so let's look at this first conditions. This omega C of summation xi is a log canonical line bundle, which is usually positive in the stable curve leading. And this part is always non-negative, so usually this is going to be typically ample. However, when curve C, when on the rational tail component, this line bundle is going to be negative on the rational tail. This is going to be as -1 degree. So that's the reason on the rational tail, this condition is a non-trivial conditions. So that on the rational tail, we require that this is going to be higher enough some degree. So E times the degree of the pullback of theta must be larger than 1. However, the absolute times of Lx must be smaller than or equal to 1. Some kind of these two conditions are kind of opposite conditions to balancing some kind of conditions to have that our modular space of E stable Quasimap to be separated. Okay, so we spread this one. So when epsilon is smaller enough for fixed degree T, we are not allowing any rational tails, and we like to talk about such a thing for any degree T, so that for such asymptotic stability conditions case, we will denote it by 0 plus. So this is a very small, so just think this is a very small number compared to the degree T. Now, denoted by the Q epsilon, the modular stack parameterizing E stable Quasimaps, the epsilon stable Quasimap. The theorem is that this modular stack of epsilon stable Quasimap is a Tilly number stack, so nice space with a natural proper morphism over the affine quotients. And furthermore, if semi-stable locus is non-singular and double has at worst LCI singularities, I can show that this modular space carries a canonical perfect observed theory. So also we heard about this notion of a perfect observed theory when the first talk. So from now on, we're going to assume that these non-singularities and LCI singularities to talk about the virtual conductor classes. So there are some remarks that, first of all, this modular spaces I defined Q epsilon going to be depending on the not only geometric target W bar Z, but also depending on this ambient space stack quotient, because the East epsilon stable Quasimap might be also landing on image, might be also here. Using this inequality, we're going to have chamber structures. So given fixed degree T, we're going to, these chambers, inside of the chamber, the modular space Q epsilon does not depending on. But when cross the wall, this wall, 1 over D or 1 over D minus 1, the modular is going to be changed. And in the first wall, the domain curve has no rational tails. And the first chamber will be called the chill plus chamber, and the last one, any rational tails are allowed as far as that rational tails has positive degree with respect to n theta, then the rational tails are allowed, but no base points allowed. In this chamber, the Q epsilon exactly coincides with stable length moduli spaces. So intuitively, when you cross the wall, one, so this one half from right to left, we are trading the rational tails of the degree n with the base points of length n. So in the one, when you cross the one, for example, so before crossing, we had, for example, rational tail with the degree 1. But when you cross the wall, this degree 1 rational tail will be contracted to becomes a base point with length 1. This contraction construction actually works family-wise well when the target is projected space Pn. So in the first space case, actually we're going to have this morphism between this modular space as epsilon is getting smaller. So here we have allowing lots of rational tail, but we are contracting and also contracting all rational tails to get these modular spaces. But in the original one, there's no direct map in here. So it's only kind of rational maps are allowed here. So that they took our next call is to compare the virtual fundamental class of this one and this one, or even middle one. But since there's no direct map from here to here, we can compare the such a thing maybe in the level of generated function level, or using this iota. So taking this map, everything will be pushed forward to here, and then compare the virtual cycles inside of these spaces. So there's some history of for fixed curve and with no markings, and absolute zero plus case, many earlier complications are known, and this one is unified then. So unified Quasimaps and linear cell models for toric targets of Kiventer and Borison-Glaser, and also Roman spaces when the target is plus minus. Also the ADHM shifts modularized spaces. That's done by University School. But varying curve and with the markings, starting point was the work of Marian Opria and Pangari Pandey in stable quasars. So when target is Quasimap, the 0 plus stable Quasimap is nothing but stable quotient, which already defined by these three authors. And inspired by their paper, Shoken Fontaine and myself did for toric case, and we've suddenly realized that the actual GRT point of view is the correct generalization of this thing, and also these other examples in here. And for the generalization of for epsilon stabilities, that's work by Bustata and Bustata. Also, Yukinov Toda treated that for epsilon stable quotients. There's a long related story in the symplectic category, which I'm not going to talk about Okay, now, so we had this very huge spaces without any stability conditions, and imposing epsilon stability conditions obtained the Taylor-Mumford proper step. As usual, we have an evaluation map to the target. So at the marking, we have an evaluation map at the marker. But the marking, since the marking is not the base point, it should be landing on the geometric target. And also, in this modular space, there is a tautological line bundle, so-called UI. That's the whose fiber is cotangent line of C at the marking XI. Okay. Now we can take the first one class of UI, so-called psi classes, and then define the Quasimap invariance. So this bracket thing, that's the nothing but the this homology class paired with some homology classes. This bottom some fundamental classes. So we have this various Chon classes and Kilpack classes. And so now my question is that how these invariants are related as epsilon and epsilon changes, and the relationship, so-called the Wilkerson formula, which I'm going to present, in a sense, generalization of many interactions of Kim-Test theorems. Remember that we had this diagram using this contraction map, also this way, contraction map, contracting rational case. So this is obtained by embedding of this GIT target inside of projective spaces. So we compare these two spaces, but they are only different on the certain boundary strata, whose elements contain the curve with the rational case. Those boundary stratas are described by another kind of moduli spaces, this one. So image of this space will be stratify the boundary strata of this space, which are different from this one. So that in this here, capital A will be index for another kind of marking A. So on that marking A, we're gonna produce a base point of degree dA. So this map, so by this map, we are changing marking A, little a, to the base point length dA. So that the degree, previous degree maybe d0 is smaller than t, but the d0 will be becomes a whole degree t after adding all degree t sub a. Okay, keeping in this mind, also we have this one similar one, and evaluation map and the infinitesimal marking A, extra marking A. So A, capital A is infinitesimal marking. So now we can show this conjecture, comparison conjecture in classical. So look, So this is a virtual fundamental class on this side, and on the right hand side, when A, capital A becomes an empty set, this term will become just the virtual fundamental class of this spaces of dignity, which we like to compare with this virtual fundamental classes. But we're gonna have a lot of correction terms described by the non-empty set A, index set A. So that correction term is supported on the boundary strata. That's what we expected, because these two model spaces are different only in the boundary strata. And the nice thing is about this conjecture is that also that correction term will be written as a kind of also Quasimap invariant classes. So we take also virtual fundamental class of this boundary strata on the right, and kept with some psi classes and gamma classes. So one key part of this conjecture is that this correction term, these classes will be independent of genus G and K. So this term will be universal, only depending on our GIT cell, not depending on genus and K. So that whenever we know the answer for this one, for like genus 0 case, we can use this. Of course, the reason for independence of GK is that we are constructing only rational tails. That rational tails are genus 0 and no marking. So that's the reason why we expect that this must be the case. So why this conjecture might be related to Miller theorem? So in the semi-positive case, this correcting class coefficient will be E Quasimap invariant, and in particularly 0 plus case, this is essentially the mirror map, which relates the flat coordinate to canonical coordinate, maybe the other way, canonical to flat coordinate. When the target becomes Calabi-Yau, comes intersection to toric point. So that that just zero Wilkerson formula will generalize the Miller theorem from the abelian to the non-abelian quotients, and from the small to the big phase space, and from epsilon 0 plus to all epsilon, and from this semi-positive to all any even channel type case. So in the remaining time, I'll just show the some evidence for that conjectures more precisely. So the conjecture is proven for genus 0 case in many examples, but in the generating function level, when X is complete section in toric variety with Grassmannian, so including Papen, Calabi-Yau, and so on. How about higher genus case? So in the higher genus case, class level is proven, but only for toric variety, semi-positive toric variety. Also, have more slice generalization of that one. But we don't have yet proof for compact Calabi-Yau threefold case for hydrogen. Yeah. So that this one only include some non-compact, only non-compact labia case are included. Some of so to get some clean description of that conjecture in the level of generating function level, let's introduce this notation T. So T is just a series of the target cohomology classes, and also we have psi classes, psi square, and so on. And then using the virtual quantum classes, we got these general functions for just C and epsilon. Here's some general function level conjecture relating the f epsilon to f infinity. So these two are same after changing insertion t psi to this fractional thing, and this fractional one, in fact, so actually this J1 and J0, so special case of J1, J0 was appeared in the previous talk of Gross and Gilbert in the name of main period. This is actually when epsilon becomes 0 plus, this will be the main period when target is Calabi-Yau complete section in toric belt case, and this will be first logarithmic period apart, so that this correction term coordinate, so mirror map relating this coordinate to that coordinate. So up to certain mirror map, these two are exactly the same. Up to some overall factors or typical two factors. And we can prove that with the Chuk and Fontaine, this is true for the Chuk case, but with some technical assumption that the target space has nice torus sections. In the Hydra's case, for the semi-positive toric right case, toric right itself case, that conjecture was true. And so in particularly, when the target is just funnel, compact toric manifold case, Quasimap events are independent on the epsilon, so they are exactly actually coincide. There's no mirror epsilon needed. First statement of this kind of corollary was established by Marian, Opria, and Pandey for J plus cases in the Quasimap, and which was also extended by Toda for any epsilon. So here are final remarks. The most interesting case, of course, the toric Calabi-Yau targets, which we prove it. So for threefold, these theorems are saying that this general function exactly coincide mirror side one, so-called B model prepotential, which expands in the near large compact structural limit point. And we also proved that this hydrogenous wall crossing holds for some non-abelian local calabian targets. However, the big challenge now is to prove the conjecture for compact calabian targets. I hope that we can report some progress on this conjecture soon. One other interesting direction is, of course, varying theta, not only epsilon. You can vary theta to get different target. And the last question is, of course, proving some real symmetry for hydrogenous G. Okay.
Any questions? Any questions or comments? Yes.
Could you expand a little on this last thing on the Calabi-Yau-Landau-Ginzburg correspondence? How this is related to this wall crossing?
So, which slide?
That's right here. That's where you mentioned the Calabi-Yau-Landau. A little further down, next one. The next slide, please. No.
Second to the last.
That one. No. Go back.
Well, you wrote, how about theta wall crossings, which is related to Calabi. This
Okay, what's the question?
So, can you expand on this a little? Why is it related to the theta wall crossing?
So, for example, in the
Use the microphone, perhaps.
So the GRT target also depends on theta, right? So for example, in the toric Dillon-Mumford stack itself case, you have a very choice of a theta. So that a target will be changed when the theta is changed. So I believe that this Quasimap invariant more functorial when you compare the invariant for theta 1 and theta 2. So for example, in the genus 0 case, genus 0 invariants are recorded by so-called J function, which are obtained by Kolmogorov-Vitti invariants. The J function of theta 1 and J function of theta 2 are not much, you can see not much relationship. But the corresponding J function for Quasimap invariants are related for theta 1 case, theta 2 case using so-called analytic continuations. So that this must be true for this kind of thing. I hope that this must be true for hydrogenous case. Just because the Quasimap invariants are more closely related to mirror symmetry side, B side. B side things are even hydrogenous part will be some kind of global thing on the Kähler modular space, which where the theta lives in.
Any other questions or comments? Let's thank the speaker again and all the speakers today.